Hello, welcome to Linear Technology's Analog Video channel. I'm John Munson and I work in the Applications Department here at Linear Technology. And today I'd like to discuss current sense amplifiers with you. Current sense amplifiers, of course, would provide you a means of instrumenting motors and other loads in your systems and discovering whether they require preventative maintenance or provide other diagnostic functions. The first product that's our basic product is the LTC6101. You can see the sense resistor, and in this case, say we have a battery, which is a source of power, and a load, which is consuming the power. The current would pass through this resistor and develop a small voltage drop on this. We amplify that, provide that to your signal processing system, be that an analog to digital converter or other signal processing functions. In this slide, we show the LTC6102, which is a similar part to the LTC6101. The difference with this, though, is that we've adopted our ultra-precise zero drift technology on this part so that the amplifier that's present here has an extremely accurate differential amplification capability. What this translates into is that you can extract extremely small signals from the R-sense resistor without any degradation in the final accuracy. It means you can operate this part in a higher gain, and it ends up being that you can provide accuracy over a bigger range of currents. This can be very useful in the case of where you have to measure a very small current and then at times have a very large current, and yet you can do both with good accuracy. The specification in the datasheet that applies to this term, which is called the input offset voltage of the part. On this part, it's less than 10 microvolts, which is over an order of magnitude better than the other parts that we have. And so this one offers the ability to have extremely low sense resistor values also. This sense resistor can now be even less than a milliohm, and you can still accurately read current with this. And the benefit of that is that now that sense resistor for a given current dissipates very little heat. You can now measure large currents in small printed circuit board space without developing a lot of heat or introducing a lot of voltage drop into your power structures. And so this part operates typically at a much higher gain. The previous slide, the gain would have been in the area of 20 to 50. The gain on these can sometimes be up to 1,000. We also are offering this part with a low power shutdown. On this slide, we show the LTC6103, which is a dual version of the LTC6101. One popular measurement problem is measuring the current in a motor when it's connected to what's known as a full bridge control drive. Now in this diagram, the control, the what we call H bridge, has these 4 power transistors, and they're driven either just continuously on to run a motor at full speed, or it's done proportionally where you provide a pulse waveform to these transistors to create different torques. And this is fully reversible even though this is running on one battery, because you can steer current. If you have, say, this transistor on and this transistor on and the other two are off, you'll get current in one direction. And if you turn those off and turn the alternate diagonal transistors back on, you can end up with a current in the other direction. Now what we want to do in this circuit is identify the current of the motor. Now since all the current for the motor, no matter which way it goes, has to pass from the battery, we can introduce a sense resistor in each half of this bridge. In this case I show 10 milliohms on each side, and if there's a current going one way in the motor, it will show up as a positive voltage drop for one particular side of the part. The other side would just basically be cut off and it would show a 0 reading. But if you take the two outputs and you treat them as a differential output, you'll get, in the case of motor current going in one direction, one of these points will be at a higher potential than the other, and if the current is going the other way, that situation will flip back around. One will drop to 0, the other one will go up. So you wind up with a signal you can take to a to D converter that has a differential input, and you can get a bidirectional readout. On this slide, we show the LTC6104. This is very similar to the previous slide, the difference being that on this part we've incorporated a special combining function inside the part so that with one single output you get a signal which goes up for positive currents and down for negative currents, rather than having two wires that are both moving at once. The way we do this is you have to introduce a voltage offset though, because we don't have any negative voltages in this system. So I'm showing a low-cost 2.5 volt voltage reference here. Basically the voltage appears as a difference from 2.5 volts when it occurs. Now in this slide I show a way of taking the basic current sense amplifier that we offer, the LTC6102, with the high accuracy that I was mentioning. Now the basic device itself is capable of operating up to 60 volts. So you can use that in telecom circuits or automotive circuits without any kind of other protection associated with it. But what if you had a really high voltage? In this case, let's say 500 volts. Now what we can do is add some external transistors, and what this circuit does is once the voltage exceeds the value, exceeds the potential of this Zener diode at 51 volts, then these transistors begin to release and allow the part to basically float along with the 500 volts, but never see more than 51 volts across the device itself. The rest of the voltage then appears across the transistor. So as you can see, we have many different amplifiers, and we can easily implement so many of these different applications with the family that we have, which includes 8 different devices. You can see all of those at www.linear.com. Thank you very much.